In our previous lesson, we introduced an equation that said the voltage across an inductor is equal to negative constant of proportionality multiplied by the rate of change of current. And this constant of proportionality is called the inductance. So if we have a circuit like the one shown here on the left, and the switch is initially open, then the current is 0, and it remains 0 as long as the switch stays open. And so the rate of change of current would be 0. And with 0 rate of change of current, there's 0 potential difference from points A to point B. But then as soon as the switch is closed, then a current starts to increase in a clockwise direction. And so if the current is increasing, di dt is a positive value, but there's a negative sign, and so the voltage is in opposition to the external battery voltage that made the current increase in a clockwise direction in the first place. And so A becomes positive and B is negative, and that polarity tries to drive a current back the other direction in an attempt to cancel out the increasing clockwise current. So some people refer to the voltage of an inductor as a back voltage. Of course, in time, if the switch remains closed for a long time, then eventually this clockwise current reaches its maximum value, and the rate of change of current goes back to 0, and you're again at a case where there'd be 0 voltage across the inductor. So this inductance is sometimes referred to as the circuit's self-inductance. And as a way to appreciate self-inductance, let's talk about the mutual inductance of a transformer. Now, a quick refresher on how transformers work. If there was a DC potential difference across the terminals of coil number 1, which we'll say has a number of windings, we can count them here, 1, 2, 3 windings, but whatever the number is, we call it N1, and coil number 2 has a number of windings, we'll call it N2. If the input voltage on coil 1 is DC, then there's a current that flows in this direction. And you can use a right-hand rule that you've learned previously to remind yourself that that would make magnetic field lines that would point in this direction internal to that coil of wire. So that coil is behaving like an electromagnet. If it's wound around an iron core, then the magnetic domains align, and that magnetism is channeled through the core, and that magnetic field then appears in the coils of the secondary. But when magnetic field passes through the cross-sectional area of the secondary, that represents flux. Although this flux would be constant in value if the current is steady on coil number 1. And of course, according to Faraday's law, when flux is constant, then the voltage you get across the terminals of coil number 2 would be 0, because you only induce voltage when there's a change in an amount of flux. So instead we talk about the way transformers work when we send an AC input. So if there's some AC potential difference across those terminals, then current doesn't just flow to the right, sometimes it flows back to the left. And so the magnetic field of the primary coil doesn't always point up, sometimes it points down, and so the magnetism that's pushed through the secondary coil sometimes points down, sometimes points up, and so now there's a continuous rate of change of flux on the secondary coil, and so there is some non-zero output voltage on the secondary. And by the way, if the input voltage is AC, then this output voltage is also going to be alternating. Okay, so one more thing about this one. If the number of coils in the secondary is greater than the number of coils in the primary, we refer to this as a step-up transformer. And so the voltage you get output on coil number 2 is greater than the voltage input. In fact, this is how much greater it is. Voltage number 2 is equal to the ratio of N2 over N1, in this case a number greater than 1, multiplied by voltage 1. So as long as N2 is greater than N1, then this number is greater than 1, and the output voltage exceeds the input voltage, hence the name step up. But while that transformer steps up the voltage, it steps down the current. After all, we can't violate the law of conservation of energy. So the power input and the power output in the ideal case are equal. Actually, quite often, the power out is a little bit less than the power in because some of the electrical energy is wasted as thermal energy as the iron core heats up. Now you could limit how much that iron core heats up if it's made out of a bunch of wafers of iron pressed together in order to reduce the eddy currents that appear. In any case, we'll assume an ideal transformer in which there's no heat loss. Power in an electrical circuit is current times voltage. So the current in the primary multiplied by the voltage across the primary has to equal the current in the secondary multiplied by the voltage across the secondary. So the ratio of V2 over V1 is equal to the ratio of I1 over I2. In other words, if the voltage is stepped up, then the current has to be stepped down by the same factor in order to maintain a steady value of power in and power out. So we name transformers step up or step down based on what they do to the voltage, but they always do the exact inverse to the current. Okay, so let's get back to this idea of inductance. What we're really saying is some amount of current being input in coil number 1 leads to a voltage being output in number 2. And so we can state this really simply and just say the larger the amount of AC current input, the greater the voltage output we should expect. So we can say that the voltage output on coil number 2 should just equal some constant of proportionality multiplied by the current in number 1. And so we'll say this is a constant that has to do with the current in coil 1. We'll call that C1. But by the way, transformers work in reverse. If we send a current in, so if our input is on coil number 2 instead of coil number 1, then we should expect to get an output voltage on coil number 1. In this case, the transformer would be operating as step down. But in any case, the output voltage we get on coil 1 in this case should be a constant of proportionality multiplied by the current input on coil number 2, meaning the greater the current being input, the greater the amount of voltage we should get on coil number 1. And so we'll say this is C2. So C2 is equal to voltage 1 over current 2, and C1 is equal to voltage number 2 over current number 1. Now let's just go out on a limb and suggest that these might be the same value, constant proportionality. If that's the case, then E1 over I2 would have to equal E2 over I1, which says that voltage 2 over voltage 1 is equal to current 1 over current 2, but that's exactly what we stated earlier when we took into consideration that an ideal transformer only transforms current and voltage, does not transform power. In other words, a transformer that steps up the voltage steps down the current by the same ratio. And so when we made the assumption that these constants of proportionality were the same, it led to an equation that we already know is true, and so this must be the case. They must be the same constant of proportionality, meaning there's no reason to call it C1 or C2, we can just call it C. And in fact, if it's the same constant for both coils, then we can say it has a mutual value, and in fact, what we mean by that is it's the mutual inductance, okay? So we can replace this by saying the voltage output on coil number 2 is equal to the mutual inductance of the two coils multiplied by the current in coil number 1. And likewise, when we reverse the direction of operation of our transformer, then the voltage we get output on coil number 1 is equal to the two coils' mutual inductance times the current being input on coil number 2. Another way to think of this is when we operate it in the forward direction as a step up, then this alternating current that's being input on coil number 1 is making coil number 1 become an electromagnet, and those magnetic field lines then get sent to coil number 2, and that's the issue, is as soon as we have magnetic field that's changing direction in coil number 2 sees that as a rate of change of flux, and by Faraday's law, a voltage is induced equal to the number of coils multiplied by the rate of change of flux. We can put the negative sign, and that negative sign is telling us that coil number 2 has a voltage across it that's always trying to cancel out the change in flux that it receives from coil number 1. So coil 1 is inducing a current into coil number 2, and the ability to get an output voltage on coil number 2 depends on how great the mutual inductance is between the two coils. So that leads us to the quantity of self-inductance. Well, we've already studied that. Instead of one coil creating the magnetic field and then a second coil responding to the change in flux, when there's only one coil in a circuit like this, when we have a battery voltage and a switch that's suddenly closed, then this coil has magnetic field that it sends not through a secondary coil, but it has a magnetic field that it sends through itself. Now, in the initial case, there's no magnetic field because there's no current with the switch open. But once we close the switch, that gets us to case number 2. A little bit of current starts to flow in a clockwise direction, and that makes some magnetism, according to the right-hand rule, appear, and some magnetic field lines start to point upward through the inductor. Well, the inductor doesn't like to have a magnetic field suddenly appear when there initially was none. So it tries to create a magnetic field back in the opposite direction to cancel out, right? So there's an induced magnetic field that tries to bring the total magnetic field back to 0. And the only way you can get a magnetic field back in this direction is if instead of having current flow this way, if you could send a current back the opposite direction. And that would happen if this terminal was positive and this terminal was negative. In other words, that current would get sent back this way to compete with the external current that made the magnetic field increase from 0 to a non-zero value. Eventually, in time, if this is a source of DC instead of AC, then it would be just like the transformer. As we said earlier, when DC is input, then the voltage output eventually reaches 0. Except in the moment when you first connect. When you very first connect the DC source, for a moment there'd be a non-zero output voltage as the flux initially changes. But once it reaches its steady value, then there's 0 output voltage. So the same is true when it comes to self-inductance. When the switch is first open and there's no current at all, the voltage is 0. When the switch is closed and it's closed for a long time, then a current flows in the clockwise direction. It reaches its maximum value. Magnetic field lines have appeared in the electromagnet and they reach a constant value, and there's no longer a rate of change of flux, and so there's no voltage. So the real question is what happens in between, right? What happens as we go from case 1 to case 2 as the switch is just being closed? There's a back EMF as indicated by the polarity of points A and B in this circuit, and that back EMF is the induced voltage of the inductor, and it's equal to negative L di dt. So in other words, the inductance is equal to the ratio of the back EMF divided by the rate of change of current.